All right, the next thing I want to talk about is we've talked about thinking about the complex numbers as representing a plane geometrically, but there's an idea from Calc 2 that's going to turn out to be very useful and very nice for us in complex. And so I want to introduce that now or remind you of that idea from Calc 2. So I'm going to take the complex plane. I kind of think of the horizontal version as the real axis and the vertical line is the imaginary axis, so we can call that x and y, just thinking of our complex number z is x plus iy. Again, just remembering that we always use, or typically use z for complex numbers, x and y for real numbers. And what I'm going to do is I'm going to pick a point here. Let's just call it x plus iy, or you can call it a plus ib, whatever you want to call it. That's fine. If you're bothered that I'm using x and y twice in two different ways, sorry about that. Just call it whatever you want. And what I want to do is I'm going to draw a triangle. And when I do that, there's a few things that we're going to notice. First of all, the angle that the line, so if you were to draw a line from the origin to this complex number z, the angle that this makes is going to be some angle that we're going to call theta. Okay, and that angle is called the argument of z. So this is the argument of z. And we denote that by arg z. And that's theta. So we've defined it to be theta. Also, the line segment between the origin and that complex number has a certain length, which we'll call r. So r is the length or absolute value, or I'll say modulus of z. And we would write that r is, we use absolute value notation even though we're talking about complex numbers. So that's the length of, that's the modulus of z. Okay, so that's the length of the line segment connecting the complex number to the origin. Now, if you remember, polar coordinates were some ideas, that was an idea that was used in Calc 2, and that's going to be a very useful idea for us here. And so if we were to think about this in terms of polar coordinates, I can think of this point as the point x, y, right, where x is the real part of z, y is the imaginary part of z. And what we can do then is we can remember a few things here. We can remember that x is going to be r cosine theta, y is going to be r sine theta, and then of course if I were to take y over x, that would give me sine of theta over cosine of theta. The r's would cancel, and so you'd end up with tangent of theta is y over x. Okay, so tangent of theta is y over x. And this is really how we convert back and forth between polar coordinates and the normal Cartesian coordinates, the usual x and y's. So that's going to be a really useful idea for us. And actually, if I write x, if z is x plus iy, and x is r cosine theta, and y is r sine theta, then what we can do is we can factor out the r, and we're left with cosine theta plus I sine theta. Okay, and so this is really going to be a useful notation for us. So z is, you can write z as r times the quantity cosine theta plus I sine theta. Now, a few things that I want to point out. If you were to take the modulus of any value like this, cosine theta plus I sine theta, the way that it's been chosen, and of course, it's kind of why we use sine and cosine, is that if you were to take the length of the line segment connecting the origin to that point, you would get 1. So in other words, this cosine theta plus I sine theta is going to be some complex number that's on the unit circle centered at the origin, okay? And it happens to be the point in the direction of the complex number. In other words, the point that's going to intersect that line segment in the unit circle. Okay, so that's that point right there, cosine theta plus I sine theta. Okay, and so it turns out that this cosine theta plus I sine theta is going to have modulus 1. Okay, so just a good thing to keep in mind, and we'll again talk about this in due time. If you were to add two complex numbers written in polar coordinates, then there's not really too much to say there. You would just add the corresponding parts. Multiplication is a little bit more interesting. So if you were to take z is, say, let's call it r1 cosine of theta 1 plus I sine theta 1. And let's say w is r2 times cosine of theta 2 plus I sine of theta 2. And if you were to multiply these together, what you would get would be, so zw would be r1, r2. And then you have to think about how to multiply inside. So the cosine terms are going to distribute over one another. And let's see, you're going to end up with cosine of theta 1, cosine of theta 2, minus sine of theta 1, sine of theta 2. I'm going to run out of room here. Plus I times, let's see, cosine of theta 1, sine of theta 2, plus sine of theta 1, cosine of theta 2. Okay, and I still ran out of room. So just a quick rearranging here. Oops. There we go. So just a quick rearranging that, just make that a little bit more visible. So that's sine of theta 1 times cosine of theta 2. All right. And I need another parentheses. So it turns out, if you remember your trig formulas, this is going to be, let's see, cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. Just remember the addition formulas for sine and cosine. And so what this tells you is, actually it tells you geometrically what multiplication by a complex number represents. So if you were to take two complex numbers, say z and w. So here's z, the argument of z, let's just call it, we called it theta 1. The argument of w, we called it theta 2. And so it turns out that if you were to compute z times w, what you would get would be the product of the two moduli, r1 and r2, so that's the length of that segment from the origin to those points c and w, times cosine of theta 1 plus theta 2 plus I sine of theta 1 plus theta 2. In other words, what you would get would be some other number, maybe something like here. And it turns out that the argument of that product would be the sum of the two arguments. So you would take, I think colors would be helpful here. You take the green part plus the red part, and then that would give you the purple part. So that purple angle is theta 1 plus theta 2. Okay, and so that's how that works. So when you multiply two complex numbers, geometrically what's going to happen is that your product is going to have the sum of those two angles, and the length of that product is going to be the product of the two lengths here. So you would take whatever this length is times that length, and then that'll give you the length of your other number. Okay, so this would be ZW. Okay, so just a good, nice geometric intuition of what's going to happen when you multiply two complex numbers. Okay, so a good thing to keep in mind. In particular, if you were to square a complex number, so if you were to think of z squared, what that does is that's going to double the angle, and then you take whatever the distance is from the origin to that complex number and you square that distance. Okay, so that's what squaring does. So good, just geometric intuition for how that works. Okay. All right, next what I want to do is I want to talk about an issue that comes up in polar coordinates. And so in polar coordinates, there's a few intricacies that I just want to explain here and what they mean in this context. If you were to take some number, say x plus iy, and you would think about this as, so z is x plus iy, or you can write it in polar form, r times cos theta plus I sine theta, then A few things just to talk about. R is the distance from the origin to this complex number, and theta is the angle that it makes. If you were to draw that line segment, it's the angle that that line segment makes with the x-axis or the real axis. Okay, so that's theta. However, there's more than one way to represent a number in polar coordinates. So for example, what you could do is you could say, let's not think about theta. Let's think instead about theta plus pi, right? So we're thinking of some other number over here, and then this would be theta plus pi. That's a perfectly valid way to do it. And then your r would be negative. You'd have to walk backwards a certain distance. So starting at the origin, you'd walk backwards that distance to get back to that complex point. We're not going to allow that in complex analysis. And when I say not allow that, what I mean is that whenever we write r times cosine theta plus I sine theta, we're going to assume that r is positive, because one of the things, and this is a consequence of what I wrote above, r is the length or the modulus of that line segment connecting that complex number to the origin. So we want to think of r as positive. So we're not going to allow that walking backwards thing like we did in polar coordinates. At least in general, when we write this, we're going to assume that this quantity r is positive. Likewise, we have to talk about what are the values of theta that we can take. And so, of course, you could take theta. You could think of this as theta plus 2 pi. So you could do theta, and then all the way around again would be 2 pi. And in fact, there's nothing to stop you from doing 4 pi or 6 pi or minus 2 pi or minus 20 pi or whatever you want. You also could think about this range of thetas is instead of being between 0 and 2 pi, you can think about it as being between, say, minus pi and pi. That's another, not quite a trick, but that's another thing that you can do in polar coordinates that gives you a little bit more flexibility, is that you can change the allowable values of theta to fit your needs depending on the problem. This choice of theta, choosing the range of theta, so I want to write this down. Choosing the range of theta has a name, and it's called making a branch cut. And there's a picture that I want to, the picture's going to be slightly mysterious for now, but I want to at least explain where the name comes from. And the idea is that if you were to have a multi-valued function, you can think of this multi-valued function. So kind of every time you walk around the circle, you're kind of going up a level. You could think about it like a parking garage almost. And you want to pick what are the values, say, between 0 and pi. So what you're going to do is you're going to figure out where do you have to cut it so that you have the values between 0 and 2 pi. Okay, so that's a completely, that's not a perfectly rigorous explanation. That's a very intuitive explanation, but that's where the idea of a branch cut comes about. Whenever you have complex numbers, it turns out you have to be extra careful when you're talking about functions. Otherwise, you could have multi-valued functions, meaning that, so unlike in functions with real values like y equals x squared, what makes it a function is that whenever you put in a value, you always get one number out, okay, and just one number. And for multi-valued functions, that's not true anymore. In fact, multi-valued functions aren't functions. They're things that when you put something in, you could get out multiple values. And so you have to decide what are the allowable range of things that you're allowed to plug into the function. And that's where this idea of a branch cut comes in. So we'll talk a little bit more about that when we talk about functions and analytic functions and continuous functions, and when we talk a little bit more there. Okay, but that's called making a branch cut. All right. Again, geometry, we talked about how that works. Let's talk about an example here. If I were to take, so consider the complex number z, what is z multiplied by I? Okay, let's think about what does that mean geometrically. And so it turns out what's going to happen is you're going to take some value z, and it's going to be some distance away from the origin. So we'll just call that r. Okay, so z could be r times cosine theta plus I sine theta. And think just geometrically, what does multiplying by I do? Well, when you multiply two numbers, you could think of I as, so I is this number up here. It's a distance 1 from the origin, and the argument of I is pi over 2, okay, or 90 degrees. And the argument for z would just be theta, okay? And so what this is going to do is multiplying a complex number by I is going to take that complex number in the plane and then rotate it by 90 degrees. Okay, so you're going to take this value and you're going to rotate it. So if this is z, then this is zi. Notice that the length, the modulus of z and the modulus of zi are the same. And the reason for that is that when you multiply two numbers, you multiply their moduli, and the moduli of I is just 1. So you just end up with this r value. So that distance here is, again, r. And then you take the value theta and you add pi over 2 to it. So the argument, I'm not going to write it because it'll be too cluttered, but that argument there would be theta plus pi over 2. Sorry about that vertical line there. Yeah, just theta plus pi over 2. Okay, so that's what happens when you multiply a complex number by I. So it's really just the same as rotating that complex number in the complex origin by 90 degrees in a counterclockwise manner. Okay, so that's what multiplying by I does.